Having me here. I always like to give talks locally. I travel a lot, giving a lot of lectures, but I always try to really make sure I get out of my own hometown since I live right here in San Francisco. We don't have that much time. Some of these talks on this topic easily stretch hours, and I know we don't have that. So 20 minutes, I'm just going to give you a quick tour of what we do in our laboratory at the Mission Bay campus of UCSF. But more than that, as you can see here in the title, I want to give you a vision of where we're going, because that's much more exciting for me to talk about than where we've been. There's so many different perspectives that guide our research. One of them that I've been favoring recently is thinking about high performance and what that means as modern humans. And one thing that we are well aware of is that when it comes to this world, the world of physical fitness, we've not just been focused on high performance, but really on optimal performance for decades, right? And if you look across all these different domains of strength, endurance, power, speed, flexibility, balance, coordination, you will find that there are specialized programs, practitioners, equipment, all devoted to optimizing. Right? And this could be from entertainment like Cirque du Soleil, from competition such as sports and athletics, wellness, health, rehabilitation. Really begging the question of what are we doing when it comes to optimizing the function of our brains. And those core abilities that really most define us as humans, right? Our attention, our memories, perception, emotional regulation, our decision making, even things like wisdom and compassion. And I would say in that regard, we're really tragically lacking in our ability to optimize. When we think about building cognition for young, healthy minds, that would fall into the domain of what we would probably think of as education. But there we see this almost completely siloed approach to transferring information content, but not really building the underlying information processing abilities of a young mind. For keeping healthy adults at a high level throughout their whole lives, we think of that as the wellness movement, right? But that, we find, has really just been largely marginalized as alternative, not really getting the mainstay of attention. And then in my world as a neurologist, when we try to boost cognition in people that have deficits in neurology and psychiatry, we have, again, a completely focused approach, probably not 100%, but largely focused on using small molecules, what we come to think of as pharmaceuticals, as tools of improving brain function. The problem is that these molecules, while they might be selective for neurotransmitter systems, are not really targeting what we now know is the underlying computational unit of the brain, which is the neural network. And therefore we have to boost our doses to very high levels to get the effects we want, and then we get just as many side effects as effects. Everyone in the field is well aware of this long-standing problem. We also have a completely non-personalized system. We make our prescriptive advice based on large population studies that ignore all the individual differences. And so we have some, I think, really fundamental dilemmas that exist right now, 2016, that I don't think we should have in terms of boosting cognition across all those populations. Driving us as a laboratory to think about innovative ways of accomplishing what I think we've largely failed to do. And for that, we could turn to technology and ask the question, does all of the amazing technology that I know you are all aware of, this explosion in information technology specifically, both its diversity and accessibility, has just opened up amazing opportunities, but it's been largely directed at entertainment, media, communication. We're really at what I would describe as a phase shift right now in terms of technology as we see the consumerization of things like virtual reality, augmented reality, motion capture, wearable physiological devices, and artificial intelligence. The goal is to think about how we might build with this technology, not just, as I described, for entertainment and communication, but to improve our function of our brains and even elevate our minds if we shoot for the highest level. So how do we do that? It seems like a really tall order for tech like this. But the reality is I don't think it's quite as complicated as it may seem, because technology, all our IT and especially these new ones, can be used to create really powerful experiences. And experiences are the gateway to our brain's plasticity, right? right? That wondrously complex dance of change, right? It occurs in all of our brains all the time at every level. Its structure, its chemistry, its function, always modifying itself in response to experience. We know very well how powerful this relationship is. Even witnessing a single tragic event can detrimentally affect the function of your brain for the rest of your life, right? PTSD. You don't actually have to get shrapnel in your brain. So the goal is to build technology that harnesses this plasticity so that we can enhance our cognition, refine our behaviors, and really elevate our thinking and our minds. That's what we're trying to do. So let's be a little bit more specific. How do we create experiences using technology? Well, in our lab, we have really focused on this one approach to technology, which we call the closed loop system. A closed loop is any type of intervention where you intervene, you act in some way, you record the impact of that intervention with as low latency as possible. So ideally in real time, you're recording what the impact is. Then you use that data to update your intervention and apply it again. Cycling and cycling, refining and optimizing at each pass, and personalizing for that situation. This could be a physical closed loop, this could be biological, but the idea is to have this very low latency, this very short feedback loop to keep refining. It's the opposite of how our current medical system works, for example. You take a pill, you go home, you subjectively monitor the effects and the side effects. Months pass, return to your doctor, and then you go up or down a little, depending on what you recorded. And that is not a very effective way to change something, especially something as complex as the human brain. So I feel like that's why we're sort of caught in this cycle of just building medications that are in the form of drugs that are not really going to have the desired effects that we're ultimately looking for. This is how we build closed loops in our lab. We build video games. You heard a quick mention of that. Video games, largely also used for entertainment purposes, but they are clearly powerful tools of behavioral influence, positive or negative. They're interactive technology that is immersive and engaging. It's engaged in globally. It's pretty much male, female now. The average age of a gamer is pretty close to 40 years old now. So it is different than it was in the 80s. And many of us feel that video games can be used to have positive impact. Now, the games that we're talking about in our lab are not off-the-shelf games. They're customized games, and they work on this model. So I'm just going to give you a little cartoon of how this works. Something occurs in your brain while you're playing one of our games. Our games are targeted to challenge the underlying systems that we're trying to optimize. While that happens, your brain responds and your body gives a response, performance. That might be recorded in how fast you are, how accurate you are. That information is detected by the game software engine in real time. And then the game feeds back an environment, which is basically a scaled challenge that's appropriate to your abilities. So without telling the game that you're 8 or 70 years old, the game will figure it out, give you an appropriate challenge, one that's not too hard, where it's frustrating, not too easy, where it's boring, hold you right in that sweet spot. And as your plasticity improves your brain function, the game will get just that much harder every single moment, pushing you into a more optimal state. This is the idea of the closed loop. We can also give feedback to create motivation and deep enjoyment in the act of training through the closed loop as well. We could then take other technologies like motion capture, which you could buy in Best Buy, part of the Kinect gaming system from Microsoft. Physiology, like all the watches that are worn all over San Francisco to collect aspects of how your heart rate or your emotional responses are evolving, and feed that into the game engine, right? Because so now the game can learn you even in a deeper way than it can just by recording your performance. We can also use new technology, and I won't go into this all now, but augmented reality, virtual reality. These will be in your awareness if they're not now. 2 massive virtual reality devices, the Oculus Rift and the HTC Vive, just went into the consumer space weeks ago. And these will create even a more real-world environment for you to engage in. And so we have this more complex closed loop, and then we could tie it all together with AI and machine learning algorithms so that what we eventually wind up with is what we consider a multimodal, so acting across multiple domains, integrated closed-loop system. This is how we believe we will be able to optimize brain function across all different populations, whether it's healthy adults or children, and we think of it as educational wellness, or people that are suffering impairment and then they're psychology or neurology, psychiatry and neurology patient. We think that this will be able to act very broadly. So let's make it just a little abstract. Again, it's a short talk, so I'm going to reduce this 5-year study down to one slide. 9 years ago, when I started on this pathway that you just saw, I reached out to friends of mine that worked at George Lucas's game company, not far from here in the Presidio, LucasArts, and I had a design of a game called Neuroracer to challenge older adults in an aspect of their cognition that we know from decades of research and over 10 years from our own lab, which is the act of multitasking. And the idea was, if we challenge this ability at a high enough level, we'll see improvement in their ability to multitask because the brain is plastic, but also other cognitive abilities that are not directly trained in the game, but because we know through our research that they're mechanistically related to each other through common networks in the brain, we would see transfer to other domains. And so what we showed in multiple studies was first that multitasking abilities decline from 20 years old to 80 years old, using the game as a very sensitive behavioral index. And that brain activity, and I'm not going into this data, also declines. And this is what we've already known from other studies, but to be able to show with a video game was unique. And then we could have a group of older adults, healthy 60 to 80-year-olds, when I say that, that's for this study what I mean, train on the game for a month, and we find that this occurs. We can improve their ability to multitask on the game, even exceeding that of 20-year-olds after just 12 hours, change their brain activity and the networks of their brain in a corresponding way, and confirm our hypothesis that we can improve their sustained attention ability and their working memory, that's memory for information over short periods of time, just through gameplay in this multitasking environment. We went on and published this in Nature, which is sort of as good as it gets for us scientists, at the end of 2013. And it was the cover of the journal, which is quite exciting to us, and really launched 2 big pathways in our lab. So this is now, several years ago. The first is that I've been working to move the game out of the lab, right? Because what you saw there is a game, but it's really a prototype of a game. It's nothing that we can sell or share. It's not at a high enough level that you would engage in if you weren't being paid to be in a research study. You need like a full, real game team to build something at that level. And so I helped co-found this company called the Gazzaley Interactive Labs with a lot of those same people at LucasArts that volunteered with us to build Neuroracer. And this game, actually was just in the news 2 days ago, is created this game. This is around 4 years now of development at a very high level, maintaining the same engine of the game that we had in Neuroracer, but building much higher levels of interactivity, art, music, story, and creating a really amazing iPad game. This game is not available to the public, which is a very polarizing reality, but it is locked down going through multiple clinical trials to try to move this game in as a full therapeutic device, like a medicine. And so right now, actually just 2 days ago, what was announced, Gazzaley launched a large multi-site clinical trial to get FDA approval for the game as a treatment for ADHD. So we'll know by next year whether or not we have a prescribable video game, which is the truth. There's also autism, PTSD, traumatic brain injury, depression, and Alzheimer's disease studies that are all underway. So that's what's going on outside of the lab. In the meanwhile, we're back in our lab, which is 15, 20 minutes from here, creating new technologies to improve brain function. So one of the other labs I started is called Neuroscape Lab. I'll show you a little bit of what it looks like, because it doesn't probably look like any lab you've ever seen. This is our new neuroscience building on the Mission Bay campus. This is our lab. So over here in our control room, we do a lot of development of new media to use closed loop approach to create these types of software. And over here, our participants engage in our tasks, often using things like virtual reality, motion capture, as I described to you. I just want to give you a quick snapshot of 4 of our games. We have 8 new ones in the lab, and we've been working, usually it takes us 2 years to build a single game. They're very, very big enterprises, how we approach them. They're not what I would call exercises where a lot of brain game companies have went, but they're a deeper, more immersive experience. And we think that that is critical for the effects that we're looking for. These are 4 of them: MetaTrain, Rhythmicity, Virtual Attention, and Body Brain Trainer. These are some images. Some are on iPads, some use virtual reality goggles, some use motion capture. They all target different aspects of cognition and use different types of game mechanics to achieve that same goal of challenging in a very targeted way these cognitive abilities and putting continuous pressure on them through these closed-loop algorithms. They all have patents associated with them so that they can leave the lab if we show that they're effective in our research studies, and then hopefully be productized and scaled and then go out into the world, both through medical and educational purposes. We do, I would say, the deepest dive anyone in the world does to figure out how they work, from MRIs to EEGs to stress testing to sleep monitoring to blood work, looking at inflammatory markers and hormone levels, all trying to understand how these games change your system and how they can be optimized and personalized for you. We do believe that the ultimate win will not happen over the next couple of years, but will really be when we advance to the stage of looking at how these games interact with each other, that you get a whole customized set of games, what I refer to as neuro CrossFit training. So I think that this combination in a personalized way is what we will see as a future medicine and educational approach. I'll conclude with telling you the sort of most forward, crazy thinking in our laboratory, which does consume a lot of our time. Pretty much all of our lab is involved in the type of work I just described to you. We have a really large lab. But we look at video games as an exciting and powerful way of activating a neural network selectively, something that we've never accomplished any other way besides an experience, an interactive experience. But we can then use neural recordings to create new approaches to what we refer to as neuromodulation and neurofeedback. In order to do that, we have to know what's going on in someone's brain in the moment while they're engaging. So we have a new technology in our lab with many partners. This was a big project known as the glass brain. If you look it up online, you could read a lot more about it than I'm going to tell you now. But essentially what it is an integration of MRI and EEG. So what you're looking at here is someone from our lab. We pretty much all have one of these now, a glass brain, looking at both the structure of their brain, and these different colored lights are different frequency oscillations of electrical activity in real time. There's just a 0.2 of a second delay here between the time that it's generated in your brain and the time that we're recording it and visualizing it. So we're still refining this technology. This is not really a movie what you're watching. We just recorded one of us with a joystick flying through one of our brains. So we get to, in real time, fly through a brain, see how it's responding to whatever situation is going on. So how do we use this type of technology? So in one slide, I'm just going to summarize everything I said and pull in the glass brain. So it's 2016, you present to your doctor. As I said before, you're 8 or 80 years old, you have a problem with your attention. You get one of these, which has the disadvantage that it's really a sledgehammer, right? It's a blunt instrument and it causes lots of side effects. We don't think that we have to get rid of these. We just think that we can manage them with much lower doses, use them as an activator, and then use an app, which is something I didn't tell you about, we're also developing, to figure out how we're going to target our intervention. What are the personal weaknesses and strengths of how your brain processes information, and then give a game or a series of games to create this closed loop, activate the network, put pressure on it. Then the glass brain comes in. We can take neural data during gameplay, locked to events in the game, and feed that into the game engine. So now the game is not just responding to your performance, how fast you are, how rapid you are, or even your heart rate, which we're doing in other games, but it's actually responding to what's going on inside your brain. So it can diagnose, for example, that you have a weakness in how you process information visually, just because it knows what the norm looks like, it knows where you were before, and then it uses that data to guide the challenge of the game and the rewards. So we think it's like a surgical approach, putting a very selective pressure on only those areas that are weak, and then when it is optimized, it moves to another, constantly, without any top-down control, moving and optimizing processing. We can also, and we have these projects in the lab as well, use EEG data to guide a brain stimulator. This is a non-invasive approach that it's really never been shown to have any dangerous side effects, but we could stimulate the brain electrically with alternating current at a very low level, like a 9-volt battery. You can only feel it for a couple of seconds, and then you actually can't feel it at all. And what this does is it oscillates with a rhythm that could match the rhythms in your brain, and we now have 2 papers coming out showing that we could speed up the learning curve if we stimulate your brain during gameplay. So you play a game with a stimulator. You can imagine if you have a traumatic brain injury, and we have a series of games that are targeting what you need to optimize, and then use this to increase the plasticity in those areas that need repair, it would be quite a benefit to that patient. So what we wind up with here is something that's now targeted to the underlying neural networks, personalized, not just to the individual, but how that person changes over time. Multimodal, right? Not this idea of like one pill is a holy grail or even one game, just an integrated across many different approaches and multiple closed loops rolling and interacting with each other. And then because almost all the time we favor consumer-facing technology over $100,000 million laboratory equipment, we will have an approach that can be used in the real world in real time. Right? As a neurologist, we always suffer with the fact that we have to take these very sparse snapshots of our patients when they come in a totally stressful environment of a clinic. Now they could collect their own data and do their own intervention at home, that all that data could go to the cloud and just be communicated directly to a caregiver or a physician or a teacher. While we incubate all of these approaches that you saw, we now roll out through multiple collaborations over the world, but many at San Francisco at UCSF, to look at how it can have benefits across all these clinical conditions. So this is not really a wish list. This has all begun. Some studies have already, advanced. Some are in the collaboration phase of grant funding. And so it's really exciting to see the potential to strengthen neural networks across such a diverse array of clinical conditions. And then we've also now launched a pretty large, and hopefully we'll get larger, program on education around San Francisco to K through 12, largely even focusing on middle school, as well as wellness programs for healthy adults. And I think that was in time, and thank you for your attention.